Assalamu alaikum everyone. So today we will be having lecture number 18 and we will be talking about signal encoding techniques. So these are the bullets or main topics which we will be going through one by one. So as in one of our last lectures we mentioned that the data transmission or data communication from one point to another point is a complex task. So what we did in order to perform this complex task, we chunked down this complicated task into different subtasks, and those different subtasks or different functions are being performed at different layers. So we followed layered approach, and each layer has its own functionality. So our different protocols, different devices, different applications, and different stuff that has to be working on different layers. So in order to have data transmission, data communication, when we talk about the wireless communication, we also have different layers, and those layers have their own functionality. So we will be looking at that at the present moment, where we are, and what we have done so far regarding the layered approach which we are following in order to have data transmission, data communication from one point to another point. Then we need to represent data, and for that data representation we need different signaling techniques. So we will be talking about the different data representations and different data encoding schemes. Then we will be talking about the reasons for choosing those different encoding techniques, why we are using those different encoding techniques, and what are their advantages and what are their disadvantages. Then we will also talk about the performance factors that are involved when we talk about the encoding schemes. And finally we will be talking about digital data and digital signaling techniques, for example amplitude-shift keying, frequency-shift keying, and phase-shift keying. And then after that we will take analog data and digital signal, and we will discuss that what are different techniques that are being used in order to have this type of data representation and signaling technique that is being used. So let's start. So we will be looking for that if we talk about the layered approach, then where we stand. So you know that we have discussed in details on transmission media, and we talked about different media type. Those include guided and unguided media, and we also talked about different frequencies, different data transmission rates that are being provided by those media types. Then we have talked about media impairments, and there are some advantages as well as disadvantages of certain media type. So we have discussed them in detail. So after that we talked about the protocols, that why we are using layered approach. If we talk about the communication, then what are different advantages, and then what are the layers, those different layers, and how the functionality is chunked down into subtasks, and those are being performed at different layers, and there are different layers. So we have taken the example of TCP/IP stack, that is a bunch of protocol. And then after that we talked about antenna and its propagation, and we have also discussed in detail regarding the different sizes, different shapes of antenna, and directional antenna, and we have also talked about different advantages and disadvantages of the underlying antennas. And we also talked about the propagation, different waveguides, and how the data is transmitted from one point to another point when we talk about the wireless communication. So antenna and its propagation and the propagation, and then the transmission media and the signaling, they are related to the physical layer, right? So today we will be talking about the different data representation and different signaling technique in order to have encoding. So that is again relevant to the physical layer. So at present we are focusing on the physical layer regarding our course, that is wireless and mobile computing, right? So here we have different data representation and different signaling technique that we can have. So here you can see we have the data, and data can be analog as well as it can be digital. So we can use analog signaling and digital signaling as well in order to transmit that data from one point to another point. So if we talk about analog data, so it means we have represented our data in analog fashion and we are using analog signaling. So it means we will be having the same spectrum as data. So data and the signaling, they will be at the same spectrum, for example telephony, and we can use different modulation in order to use some of the carriers, for example amplitude modulation, frequency modulation and phase modulation. Then if we have digital data and we want to use analog signaling, so in that case we have to use a converter, that is a modem that has to be modulate the data, and on the receiver side it will be performing demodulation. So the examples are ASK, FSK, frequency shift keying, ASK, amplitude shift keying, and PSK, phase shift keying. So this is the case when we have data that is digitally represented and we are using analog signaling in order to transfer our data from one point to another point. Then we have, if we have the scenario where we have analog data and the signaling is digital, so again we have to use a codec, and the example is pulse code modulation. And in the last case, if we have digital data and the representation is also digital, so we have different encoding schemes in that regard, like NRZ, non-return zero, and then we can have some other more complex techniques, and these are Manchester coding. So here you can see we have sum up the previous slide, so you can see that analog data and analog signaling. So the example, best example can be the telephone lines, but we have to use a carrier in order to transfer this analog voice from one point to another point, and then on the receiver side again that carrier has to be extracted or filtered out. And then if we have digital data and analog signaling, so again here we can use modem. So this is another scenario where you can see analog signal, analog data and digital signal. So analog data has to be represented, and we are actually using codec in order to have the digital or digitize the data. Then digital data and digital signal, so in that case we actually are using different schemes, right? So here you can see we have mentioned the treatment of the signal, how the signal has to be treated when we talk about so analog signal, and this is the transmission, right? So through amplifiers, so we have to use amplifiers, same treatment whether signal is used to represent analog data or digital data. So if we have digital signal and we want to use analog transmission, so that is probably not used. And then if we have analog signal and digital transmission, so it assumes that the analog signal represents digital data. Signal is propagated through the repeaters. So again, here we are using amplifiers. So here we are using repeaters. So you can see the advantage, because in case of amplifiers there are more chances of noise, and in case of repeaters there are little chances of noise. So this is a big advantage. Are recovered from inbound signal and used to generate a new analog outbound signal. Then if we have digital signal and digital treatment, that is digital transmission, a stream of ones and zeros represent digital data, or maybe an encoding of analog data is, so again repeaters, at each repeater stream of ones and zeros is recovered from inbound signal and used to generate a new digital outbound signal. So we also have advantage over here. So here we'll be talking about the advantages, right? Different combinations of data representation and the signaling techniques which we will be using. So if we have analog data, so you can see that we have analog signals and digital signaling as well. So in case of analog data and analog signal, we actually are using the transmission channel efficiently, right? So for example, we can give the example of FDM, frequency division multiplexing, right? And if we have analog data and digital signaling, in that case we can use the latest switching and transmission techniques, right? So if we have the analog data, for example, if I have to transmit my voice at a longer distance, right, and I will be using digital signaling, then I can use the latest transmission and switching techniques in order to transmit the voice. And then in another scenario, when we have digital data and we have to use analog signaling, so in that case the transmission media will only propagate along analog signals, right? So then if we have digital data and digital signaling, so that's you can say, because most of the equipment and the media, they support digital data, so moreover they are available cheaply, or the cost is on the lower side, so it's less complex. Cost is on the lower side than digital to analog modulation equipment, because they are costly and they are complex also. So here we have mentioned some of the examples. Digital data and analog signal, we can take the example of a modem. So then digital data and digital signaling. So this we can see whenever we talk about the wired local area networks. So you can see the computer is producing digital data, and we are using different interfaces, and those interfaces, they actually are using digital signaling in order to transmit data from one point to another point. So the wired LAN is an example of digital data and digital signaling. Then we have analog data and digital signaling, that is codec, and the examples are FDM, frequency division multiplexing, and in case of fiber optics we use wavelength division multiplexing. So this is again an example of analog data and digital signaling, time division multiplexing when we are allocating time slots to each channel, then PCM pulse code modulation, and this is being used in T1 links, and finally the delta modulation. So if I have to conclude, so in general, when the outcome is a digital signal, we use an encoding process, right? And when the outcome is an analog signal, we use a modulation process. So there are some of the reasons that why we choose encoding techniques in order to transmit data from one point to another point. So if we talk about the digital data representation and digital signaling technique that is used in order to transfer data from one point to another point, so in that case equipment is less expensive, less complex and less expensive than the equipment that is used in order to have modulation, right? That involves digital to analog scenario. And then when we talk about analog data and digital signal, then it use modern digital transmission and switching equipment. So this is again the reason for using encoding schemes. Then if we talk about digital data and analog signal, there exists some of the transmission media that only support analog signaling. So in case of fiber optics, which we use in order to have data transmission for longer distances, or you can say Atlantic oceans communication, or maybe from country to country, or maybe from city to city communication. So we normally use fiber optics because they support huge amount of data transmission, and we can transmit data at longer distances. So in that case, we have to stick this scenario where the data is digital and we are using analog signaling techniques, because some of the media that are important in order to have communication from city to city, country to country, and from one Atlantic to another Atlantic. And then in the last case, when we have analog data and analog signal, right? So is in electrical form can be transmitted easily and cheaply. So one of the example is voice transmission over copper pair. So there are certain criteria which we will be talking about, and how we find that this encoding technique is good for us, or what are the factors that determine the performance of the underlying encoding technique. So we will be talking about them. First, signal to noise ratio. So this is one of the important factor when we talk about the signaling technique. And then the data rate. Obviously we wish that the signaling technique that is going to be used, it should support maximum data rate. And then the bandwidth. This is also one of the key factor when we talk about the wireless transmission from one point to another point. So these are the three important factors, and they actually determine how successful a receiver will be in interpreting an incoming signal, right? And then an increase in data rate increases bit error rate. So this is of course is true, because we want to use the signaling technique that normally offers or present less bit error rate, because whenever we increase the data rate, there are more chances that more bit error will be occurring. So increase in the signal to noise ratio, this is the remedy. So increase in the SNR, signal to noise ratio, it will surely decrease the bit error rate. And of course, if we want to increase the bandwidth, so we have to increase the data rate. So then we can also compare different signaling techniques on certain parameters, because here we have mentioned different characteristics which we have to take into account when we talk about the signaling criteria. Then, so these are the factors, they actually are being used in order to compare different encoding schemes. Right? Signal spectrum, lack of higher frequency components, less bandwidth is required, and if with no DC component, AC coupling is possible. So these are the factors which we will be looking for when we have to choose the encoding scheme. Then transfer function of a channel is worse near the band edge. Clocking, clock actually help us in order to recognize the start and the end of a bit, right? So if we have a clocked data, then it will be easily recognizable, right? So ease of beginning and the end of each bit position. So these are the factors which we can use in order to compare different signaling techniques, encoding schemes. So signaling spectrum and clocking. And here we have some more: signal interference and noise immunity. So of course, if the encoding scheme is more immune to noise, when we talk about the communication, so we will be choosing that scheme that is more immune to noise. Performance in the presence of noise. So of course, it should perform better in the presence of noise, because noise is omnipresent and we cannot avoid noise when we have to transmit data from one point to another point, especially wirelessly. Then cost and the complexity. So of course, we don't want to invest more, so we will be looking for the encoding schemes that can be implemented at a lower cost and without introducing much complexity. So higher the signal rate to achieve a given data rate, the greater the cost. So of course, this is the key factor when we talk about the link budget. So whenever you are preparing the link budget, so this is always true: the higher the signal rate to achieve a given data rate, the greater the cost. So we want to have a trade-off between choosing an encoding scheme and the cost and the complexity. So here we will be having some of the basic encoding schemes that are being used. So the scenario over here is we have digital data representation, and the signaling that is being used in order to carry the data is analog. So we have amplitude-shift keying, ASK, amplitude difference of carrier frequency, and then on the second number we have FSK, frequency shift keying. So in spite of amplitude difference, we have frequency difference near carrier frequency, right? And then we have phase shift keying, that is the phase of the carrier is shifted. So we will be shifting the phase in order to represent digital data. So digital data means 0 and 1, so we will be having one phase for one angle, one bit, and another phase for. So here you can see the example. We have the data 0 0 and 1 1 0 1 0 0 0 and 1 0. So this is the data, and this is digital data, and we have to represent this data by using the analog encoding schemes which we have mentioned over here: ASK, FSK, and PSK. So you can see we are representing 0, right? And then you can see the change in the amplitude when we are having 1. So again 0, and whenever we have a 1, there is a change in the amplitude, so, or shift in the amplitude. So this is the shift, right? And again here 0, 0, 0, and whenever we have a 1, there is a shift in the amplitude. And then we have BFSK, binary frequency shift keying. So you can see one frequency for zeros, and then another frequency for the binary 1, right? And then again one frequency for 0, that you can name it this frequency for 0 representation as F0, and then you can name this frequency as F1 for binary 1. So this is binary frequency shift keying, and here we have binary phase shift keying. So this is binary 0, and here again binary 0, and whenever we have 1, you can see the phase shift in order to represent binary 1. Again 1, and there is again a phase shift in order to represent the from 1 to 0. So each time there is a change from 1 to 0 or 0 to 1, you can see that we will be having a phase shift. So here we have the mathematical representation of the underlying signaling techniques. So for amplitude shift keying, one binary digit represented by presence of carrier at constant amplitude, other binary digit represented by the absence of carrier. So if we go back, so you can see no carrier, absence of carrier, and 1 is represented by the presence of carrier. So this is the signal represented in time domain by S of t. So this is the amplitude, and this is the cosinusoid, and F is the carrier frequency, Fc, 2 pi Fct, and this is representing binary 1, and the absence of the carrier is representing binary 0. So here we have different advantages and different disadvantages of ASK, amplitude shift keying. And so it's susceptible to sudden gain changes, inefficient modulation technique. So this is not an efficient modulation technique. So it is being used on voice grade lines, and it can represent 1200 bits per second. So it's used in order to transmit digital data over analog lines or over fiber optics. So binary frequency shift keying. So as we are representing digital data, so we have to represent ones and zeros. So two binary digits represented by two different frequencies near the carrier frequency. So here we have the signal S of t and A cos 2 pi f1t, one frequency, that is f1, in order to represent a binary 1, and we are using another frequency f2 that is used in order to represent binary 0. So f1 and f2 are offset from carrier frequency fc by equal but opposite amount. So you can see that one frequency for 0. So if I have to calculate the time period, so you can see the difference for this frequency, and then in order to represent a 1, so you can also calculate the frequency and time period when we talk about the 1, right? So one frequency is used in order to represent a binary 1, that is f1, and f2 is used in order to represent a binary 0. So here we have some of the pros and cons of binary frequency shift keying. So it's less susceptible to error than amplitude shift keying, and on a voice grade line it is offering 1200 bits per second, and it support higher frequency, and the range is from 3 to 30 megahertz, and can be used for radio transmission. And we can also use this in order to have communication over LANs, and those LANs, they are actually using coaxial cable. So here we have multiple frequency shift keying, MFSK. So more than 2 frequencies are used, more bandwidth efficient but more susceptible to error. So you can see the mathematical operation for MFSK. A cos 2 pi FIT, where I is greater or equal to 1 and lesser equal to M. So here we have the expression for Fi. Fc, that is the carrier frequency, plus 2i minus 1 minus M MFD. So here we have mentioned different frequencies: Fc carrier frequency, Fd that is the difference frequency, number of different signal elements, and these are 2 raised to power L. L is the number of bits per signal element. So to match data rate of input bit stream, each output signal element is held for, so this is the hold time, and this hold time is equal to L t seconds, where t is the bit period and the data rate is 1 over t. So one signal element, it can encode L bits. So again, in order to accommodate MFSK, we need bandwidth to MFD, minimum frequency separation, so we need a frequency separation to FD is equal to 1 over TS. Modulator requires a bandwidth of, so total bandwidth required by the modulator in order to accommodate MFSK is WT 2 raised to power L over LT is equal to M over TS. So here we have another encoding scheme or signaling scheme, that is phase shift keying, PSK. So 2 levels PSK, binary phase shift keying, uses 2 phases to represent binary digits. So we can have S of t, A cos 2 pi f ct in order to represent a binary 1, and then you can see the shift in the phase by pi. So A cos 2 pi f ct plus pi binary 0. So if I use trigonometry, then I can have A cos 2 pi f ct and minus A cos 2 pi f ct for binary 0. Then we can also have another type of PSK, that is differential PSK. So phase shift with reference to previous bit. So we will be looking for the previous bit. So binary 0, signal bursts of same phase as previous signal burst 0. Binary 1, signal bursts of opposite phase to the previous signal burst, right? So here we have 4 level PSK. Each element represents more than 1 bit, right? So previously we have represented only 2 bits, 1 and 0. So you can see that we are actually using 2 representations, one for binary 0 and one for binary 1. So here we have to represent more than 1 bit. So for 1 1 I have used 2 pi fc plus, so this is the phase shift, and then for 0 1 I have another phase shift, for 0 0 we have another phase shift, and for 1 0, so if I 0 0 0 1 1 0 and 1 1, so we are actually representing 2 bits. So multi-level phase shift keying using multiple phase angles, with each angle having more than 1 amplitude. So multiple signal elements can be achieved. So we have D is equal to R over L, and D is the modulation rate, that is also the baud rate, data rate, R is the data rate, bits per second, and M is the number of different signal levels, right? So 2 raised to power, if we want to represent 2 bits, so M will be 4, number of bits per signal element, right? So if in order to represent 1 bit, so we will be having only 2 different signal elements. If we want to represent 2 bits, that is L number of bits, so 2 raised to power 2, 4 m will be 4. So here we have m is equal to 4. And here we have the performance expression, bandwidth of modulated signal. For ASK and PSK, we have BT is equal to 1 plus R into R. And for FSK, bandwidth is 2 delta F plus 1 plus R, small r into capital R. R is the bit rate and how signal is filtered, and delta F is the difference of frequency F2 minus FC, and then difference of the F1 from the carrier frequency. So again, performance bandwidth of modulation signal, so for MPSK, for MFSK. And before we are using actually Amplitude-Shift Keying and Phase Shift Keying individually. So here what we did, we have combined Amplitude-Shift Keying and Phase Shift Keying in order to have QAM, Quadrature amplitude modulation. So the advantage is 2 different signals sent simultaneously on the same carrier frequency. So this is the advantage. So here we have ST, D1, T cos 2 pi FCT, and D2, T sin 2 pi FCT. So, you can see that binary input, that is R bits per second, 2-bit serial to parallel converter. So here we have D1T and D2T, and you can see a phase shift over here, and this is the carrier oscillator which is generating local carrier. So this D1T is multiplied by cos 2 pi FCT, and this D2T is multiplied by sin 2 pi FCT, and then we have added these 2 signals, and we are actually transmitting this signal over the channel. So there are certain reasons in order to have analog modulation. When only analog transmission facilities are available, so of course we have to go for the analog modulation, digital to analog conversion required. So we need to convert the digital signal, digital data, in order to have the analog output. Analog signal high frequency may be needed for effective transmission, and modulation permits frequency division multiplexing. Okay, and then we have some of the basic encoding techniques, and these are AM, amplitude modulation, and angle modulation, that is the frequency modulation and phase modulation. So for amplitude modulation, you can see we have the mathematical expression 1 plus NA xt cos 2 pi ft, and this is the carrier that is used in order to vary the amplitude of the actual signal that is carrying data. So this signal has to be multiplied with this carrier. Xt input signal, and Na modulation index, that is the modulation index. So here we have the spectrum of the modulated signal, and here we have the spectrum of the AM signal with carrier at Fc. So this is the carrier frequency, lower sideband and the upper sideband, and this is the transmission power calculated. Pt is equal to carrier power 1 plus Na square over T. This is the mathematical expression in order to calculate the transmitted power in case of amplitude modulation. So single sideband variant of AM is single sideband sends only one sideband, and it eliminates other sidebands and carrier, and there are certain advantages and disadvantages. Those are associated with SSB, single sideband. Only half bandwidth is required in order to achieve the same data rate, and of course we need less power. There are some disadvantages of SSB. Suppressed carrier can't be used for synchronization purpose. And then we have angle modulation. There are 2 different types of angle modulation, that is frequency modulation, and phase modulation. So here we have signal AC cos 2 pi fc t plus phi of t, phase modulation. Phase is proportional to modulated signal. And then we have frequency modulation. So this is the expression for the, so derivative of the phase is proportional to the modulated signal. Taken the derivative of this, right? And here NF is the frequency modulation index. Angle modulation compared to AM, FM and PM results in a signal whose bandwidth is also centered at FC, and it has a magnitude that is much different. Angle modulation includes cos phi t, which produces a wide range of frequencies. Thus, so as a result, FM and PM requires greater bandwidth than AM. So here we have another scenario that we have analog data, that the data representation is analog, and we have to use digital signaling technique. So we have two different choices over here. One is pulse code modulation, PCM, and the other one is delta modulation. So once analog data have been converted to digital signal, the digital data can be transmitted using NRZL. Non-return 0 can be encoded as a digital signal using another code, that is NRZL, to the analog data using previously used techniques. So here we will be talking about PCM, pulse code modulation. Each analog signal is assigned a binary code. So first we actually will be sampling the data, right? And then we will be assigning codes to those different samples. So analog samples are referred to as pulse amplitude modulation samples. The digital signals consist of a block of n bits, where each n bit number is the amplitude of the PCM pulse. So here you can see we are actually encoding, taking the samples, right, at different times, and then after taking the sample we are assigning different codes, right? So, and this is the digit binary equivalent, and this is the PCM waveform. So we have 16, 0 from 16. So 4 bits are required in order to represent those different samples. So then we by quantization process, the original signal is approximated, right? So you can see here we can approximate by using the quantization. If so, which value we so you can say the round off, and then of course this quantization factor, it can introduce noise, because when we will be doing rounding off, then there will be some noise, leads to quantized noise. Signal to noise ratio for quantizing noise is SNR dBs 20 log 2 raised to power n plus 1.76 dB, right? So that comes out to be 6.02 n plus 1.76 dB. So each additional bit increases SNR by 6 dB, or a factor of 4. So let's have more details about pulse code modulation that we studied in last couple of slides. So here you can see this is the most common technique when we talk about conversion from analog to digital data. So we have the analog data representation is analog, and we want to digitize that data in order for its transmission from one point to another point. So this is one of the technique that we can use, that is called pulse code modulation. And there are number of steps which we have to go through. First of all, we have to convert the data from analog to digital. So we need a converter circuit that will be converting the analog data into the digital sampled, right? So that circuit is actually sampling the data, and then after taking the samples by using the circuitry, we have to perform the quantization process, right? So you can also say that this is a sort of round off, right? So if we have a value that is very close to the nearest one, so we will round off. So here we will be performing, or we will losing some sort of data. And then after the quantization, we have to assign codes to the quantized values. So here is the block diagram of the underlying PCM. So you can see we have the data. So this is the data that we have to, and we want to digitize, and we are using PCM encoder in order to encode this data. So here is the sampling, right, block and quantizer, right? So here we have the PAM signal. So we will be having pulses like this over here, and after having those pulses, right, or those samples, we will be performing quantizing process by using this quantizer, this one, and after that we will be assigning codes to those different quantized values. Okay, so here we have more details. Signals are sampled every TS second. The TS is the sample interval or the period. So the interval of the sampling interval, right, that is TS, right. So we have different sampling methods we can adopt. First one is the ideal, which is not the practical one. Then we have the natural sampler, and finally, or lastly, we have the flat top. So here you can see an ideal sampling pulses from the analog signal are sampled, right? So if you look at the images over here, so here we have the ideal sampling, and that is not possible, right, in real scenarios. And this is the sampling time interval. We have TS interval between each sample, and this is the analog signal. And then here we have the natural sampling. Okay, so this you can see the top of this sample that is shaping itself according to the signal, and that is again very difficult to achieve, right? And here is the flat top sampling, right? High speed switch is turned on for only the small period of time when the sampling occurs, sequence of samples that retains the shape of the analog signal. Most common sampling method called sample and hold, right? So here you can see if I'm taking sample at this point in time, so I will be holding this for a predefined amount of time. So then I can have a proper flat top shape over here. So this is, I'm taking sample over here and I'm holding this sample for this amount of time. So this is the flat top sampling method. So we have three different mechanisms for sampling, and there is a relationship between the sampling rate and the frequency, right? So we can sample a signal only if the signal is band limited. This is the first requirement. Signal with an infinite bandwidth cannot be sampled. So as we theoretically we say that the signal have infinite frequency components, so it is having infinite frequencies, but most of the time, or in all the cases, I must say, the first four components, they actually contain most of the power of the signal. So that's why whenever we have to deal it theoretically, or when we are performing signal analysis by using Fourier transforms, so we take the first 3-4 factors that contain most of the energy, and we ignore the other. So actually we have every signal has infinite frequency components, but effectively first 3-4 components, they are actually holding the major portion of the power represented by the signal. So that's why we keep them and ignore the rest of the signals, right? So there is a relationship between the sampling rate and the signal bandwidth, the effective signal bandwidth. So this is the one condition: the sampling rate must be at least 2 times the highest frequency, not the bandwidth. Analog signal is low pass. We can have the low pass analog signals. The bandwidth and the highest frequency are same value. Analog signal is band pass. The bandwidth value is lower than the value of the maximum frequency. So here we have the F minimum, F maximum. So it's low pass signal. So Nyquist, we have to follow Nyquist criterion over here. So the sampling rate should be twice the maximum frequency. So here again you can see if we have band pass signal, right, the sampling rate again over here is twice the maximum frequency. So let's have an example to have more understanding about the bandwidth and the sampling rate. Low pass signal has a bandwidth of 200 kilohertz. What is the minimum sampling rate for this signal? So now the bandwidth of the low pass signal is between 0 and F. F is the maximum frequency, therefore we can sample this signal at 2 times the highest frequency. Okay? So 200 kilohertz. Sampling rate is therefore 400,000 samples per second, because 200 kilohertz, so twice the maximum frequency. As if we talk about the second case, we cannot find the maximum sampling rate in this case because we don't know the bandwidth start or end, where it is starting and where it is ending. So we need that bandwidth in order to fix the sampling rate, or in order to have the upper limit. So here is another mechanism. So after getting the pulses, we have to perform the quantization process over there. So if we talk about the pulses, so these are the pulses we got after the sampling, and now we will be performing the quantizations. So these are the normalized PAM values, right? So you can see we have, this is the 0 level, D minus D, 2D minus 2D, and these are the levels. And after that we are having normalized quantized values. So here we have 1.50, 0.50, 3.50. So we are actually having some sort of process to be followed in order to have normalized quantized values, 2.50. And here we are actually the loss is introduced over here. We have to do that. And then these are the errors, differences, right? And then these are the quantized codes. We assign different codes. So you can see these are different quantized codes. And here is the encoded word. So this is 2. And if you calculate the decimal equivalent of this binary, so this is 2. So let's do it here. 101. So we are using 3-bit code. So 2 to the power 0, 2 to the power 1, 2 to the power 2. So this is 1, this is 0, so it has 0 weightage, plus 0, and this is 4. So 5 is equal to 5. So here we have 5, and all ones 7, 7, and this is 6, 4, 2, 6, and this is 2, and this is 1. So here we have the PCM quantization process over here. And then of course this is on the receiver side, transmitter side. We have encoded by using PCM. On the receiver side we have to retrieve the data. So the recovery of the original signal requires the PCM decoder. So here we are on the transmitter side, we are using encoder or coder. and on the receiver side, on the transmitter side we are using encoder or PCM coder, and on the receiver side we have to use PCM decoder. Uses circuitry that convert code words into pulses, right? So now we are going to follow the processes in the reverse order which we have performed at the transmitter. So here you can see that until the next pulse arrives, right? After the staircase signal is completed, it is passed through a low pass filter to smooth the staircase signal, right? And then the filter has the same cutoff frequency as the original signal. So this is again important at the sender. So there should be a synchronization. If the signal has been sampled at the Nyquist sampling rate, and if there are enough quantization levels, the original signal will be recreated, right? So here is the mechanism which we have to follow in order to retrieve our original signal. So let's have a question from this underlying PCM. So we have a PCM encoder that accepts a signal with a full scale voltage of 10 volt and generates 8-bit codes using uniform quantization. The maximum normalized quantized voltage is 1 raised to power to 1 into 1 to 2 raised to power minus 8. So we have to find out the step size, normalized step size, and then the actual step size in volts, and then after that we have to find out actual maximum quantized level, because we have to perform quantization, and then finally the normalization, and then the actual resolution, right? And finally we have to go for percentage resolution. So here is the solution, and you have to go through to this solution by yourself. Then we have the delta modulation. So analog input is approximated by staircase function. So it's another type of function. So it moves up or down by one quantized level delta, right, at each sampling interval. So if there is a 0, right, so it will move up. If there is a 1, it will move up, and in case of 0, it will move down. So the step size is delta, the bit stream approximate derivative of analog signal rather than amplitude. 1 is generated, function goes up, and 0 is generated if the function goes down, right? So you can see function goes up, mean we are, so here zeros, right? So you can see 1, and here we have zeros, right? And then again 0, 1, 0, 1, and then again. So analog, this is the actual signal, and this is the encoded signal, delta modulated output. So there are two important parameters when we talk about the delta modulation: size of the step assigned to each binary digit, delta, sampling rate, and as a result, accuracy improved by increasing sampling rate. So if we have more samples, right, so of course we are in a better position in order to have the encoded signal that is very close to the real signal. So of course if we increase the sample rate, so that will also increase the data rate, so we have to manipulate more data. So the advantage of delta modulation over the PCM pulse code modulation is the simplicity of its implementation. So here we will be talking about why the digital signaling techniques are being used in order to achieve data communication. One of the main reason is that nowadays most of the systems for data communication that are being used, they support digital signaling techniques. So that's why they are becoming popular, and they are being used widely all over the world. And the second reason is that when we have a digital signaling technique, so we need to use repeaters instead of amplifiers. So if we talk about the amplifiers, right, so we are transmitting data from one point to another point, and we have to amplify the signal after a certain distance. So of course the noise is always in the signal, so that noise is also got amplified. So then when we receive the signal at the receiver, so it's very difficult to retrieve the original signal in some cases, right? And if we talk about the digital signaling systems, then we have to use repeaters, and repeaters, they don't introduce additive noise. They receive the signal and then they retrieve the data and then repeat that data accordingly. And then another reason is that we use TDM instead of FDM. So no intermodulation noise, because if we talk about FDM, so we have different frequency components, and those different frequency components, they are being modulated differently, and of course there can be intermodulation noise. So in case of digital signaling technique, we are using TDM, so we don't have to face intermodulation noise. And then conversion to digital signaling allows use of more efficient digital switching techniques, right? So that's all, and today we talked about the layered approach according to our course, and what we have studied so far. If we talk about the communication, taking into account those different layers, so we are mainly focusing on physical layer or maybe data link layer, and then we talked about different data representation methodologies and the techniques that are being used in order to transmit that data, right, signaling techniques. And then what are different encoding schemes, and what have their advantages and disadvantages they are providing, and then there are different performance factors, and on the basis of those different performance factors, we actually choose one of the, or decide one of the signaling technique. And then we talked about different digital data to analog signaling techniques, and we have discussed ASK, FSK, PSK, and then we talked about analog data to digital signaling technique that includes PCM and delta modulation. And finally we discussed that why digital signaling techniques are being used widely when we talk about the data communication. So that's all. आज के लिए इतना ही काफ़ी है. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफ़िज़. अस्सलाम वालेकुम.